And let's see, current slide. And let's see, was that Madison? Is that right? Okay. Okay. Good attendance tonight. Way to go. Now, before we get going where we left off last time, let me say this. It's already come up once. If you do have to leave early, there's a good chance I'll be passing out the second test tonight. So if you want an extra week to work on it, pick it up before you go. Okay? Even if we don't quite finish the chapter, which I think we will, you'll still have most of the questions you can be working on now. Since we only meet once a week, that's only give you all the chances that you can. All right. Any questions on anything we've done so far? Okay. We left off last time. We finished 8.2, which was, find the actual title of it. It had to do with work. No, power. Okay. Now we're moving to 8.3, which deals with energy. So we've had, I don't really care too much for the way they've organized this, but it's fine. Work was the first thing we talked about. Okay. Then the time rate of change of doing work is the second thing we talked about, power. And now we go back to energy, which is the ability to do work. And that's in 8.3. And that's exactly the title that's given here. I don't know if everybody has books or not, but in case you don't, let me write that definition down for you, or at least come close to doing. Okay. Energy, one sort of simple definition of it is the ability to do work. Okay? And work is the use of energy to move things, okay, to get things to happen. All right. Now we're going to be talking about, well, I'll start here. There are many forms of energy. I mean, I'm not even sure I could list them all. Here's a few that they list here. Mechanical energy. That's lifting things, moving things around, mechanical energy. Electrical energy, plugging into the wall, getting things done, generating power. Batteries, electrical energy. Thermal energy, okay, that's often called heat, but heat is a transfer of energy, but thermal energy. Fluid energy, that's a little obscure, but we'll talk a little bit about that in another chapter. Chemical energy, big time, okay? Right now, I bet you, I know, your bodies are converting food energy, chemical energy, into the ability to see, to hear, to move your muscles, that type of, and to think, okay? Chemical energy. Atomic energy, we hope none of that happens in this class, but it's happening all around. We may be using electrical energy that came from atomic energy. And then one that you'll be near and dear to your heart, I take it, is sound energy, acoustic energy, because that's what you're going to be measuring, okay? So all these are forms of energy, and that's not all, okay? There's many others. Now, the first one we mentioned was mechanical energy. Now, if a body or a system has mechanical energy that can express itself in one of at least two forms, and that's what we're going to talk about to begin with. The first of these is due to the object's or the system's position. Okay? Now, the dumb definition I usually give of this, because energy is the ability to do work, right? Okay? Now, if I chose to do some work on, I want to say ransom, I don't think that's it. How do you pronounce your name? Perhaps in the wrong class. Oh, I can't find you now. Rance. Okay, Rance. If I wanted to do work on Rance's foot, I could take this book and drop it. Okay? but I could do that, and it would do some work on his foot. Now, would it do more work if I dropped it from here, and he didn't get his foot out of the way in time? Definitely, okay? You see the energy of position changes from here to there. That's one kind of mechanical energy that we could have, okay? The energy of position. Another is the energy of motion, because as soon as I release that book, it starts moving, okay? And then it's changing its energy of position to an energy of motion, okay? And then you can also have a change in the internal structure, and that's usually something that's going to produce heat or other things like that, change of that. So two kinds of mechanical energy, and these are, so we're starting with mechanical energy. I'm getting wrapped up in my cords here. Mechanical energy. Two kinds, okay? The first of these is potential energy. And the second of these is kinetic energy. We've run into that word kinetic before. Does anyone remember? Friction. Moving friction is kinetic friction. So, energy of motion is kinetic energy. Kinetic means that, okay? So, potential energy is the stored energy of a body due to its internal characteristics or its position. Stored energy of a body. Now, when I say body here, you can also have system, okay? Stored energy of a body or a system due to its internal characteristics or its position. I'm going to run out of room. Characteristics or its position. Okay. Now, we're going to start with position part. Okay, and we'll say potential energy is the energy of position. But it can also be internal structure, internal characteristics. For instance, that food you ate, lunch or whenever you ate it, that now your body is metabolizing, it is releasing, it had stored chemical energy. We mentioned chemical energy before, stored chemical energy that's now being transferred to be energy of something else. That is potential energy as well. Energy due to the internal characteristics. Now, as soon as you start metabolizing it, you're breaking down the chemical compounds. One of the things that's produced is heat. And that's why every one of us has a temperature. The room is probably right around 70 degrees. We're right around 98.6 degrees. 20-something degrees, almost 30 degrees higher than the room temperature because we're metabolizing. But that metabolism also enables us to move, to think, to do, to speak, to hear, to see. Everything we do comes from transferring the stored chemical energy in the food that we're metabolizing to this. That's another form of potential energy, potential chemical energy. We're going to focus on the energy of position. Kinetic energy, on the other hand, is the energy due to the mass and velocity of a moving object. I think they say due to, yeah. They like due to, I don't know. Due to the mass and velocity of an object. Now, it says object, but again, think system. It could be a system motion as well. the shorthand energy of motion, okay? Because if an object is moving, it has motion, okay? So the energy of motion. If it has a velocity, it has motion. Now, the internal potential energy, this is what I was talking about before. First, the internal potential energy is determined by the nature or condition of the substance. For instance, gasoline has internal chemical energy that when you burn it, you can move a car with it, okay, or something else, okay? And we'll be using this a lot. Compress a spring, it pushes back on you. Stretch a spring, it pulls in on you, okay? Spring has potential energy. That's more of a position type situation, okay? Those are both coming from the internal potential energy of that in the spring, in the food, in the whatever, okay? Gravitational potential energy is the one we're going to be focused on a little bit more, and that would be how high you have lifted the object. Now, when I lifted the object over Rance's foot, I was doing work on the object, changing its position, which was also increasing its potential energy to do damage to his foot, which is not what I wanted to do, but it would have. Okay. So, that is the position due to, determined by the position of an object. Relative to a particular reference frame. So, the energy of position, gravitational potential energy, is always given relative to some position. Okay? Now, my book again, but this time it won't be around Rance's foot. What if I'm holding the book over this table here? Now it has a certain gravitational potential energy relative to the podium here. But that would be a little different from relative to this table, because it's higher above the table than it is here. And that would be a little more than the distance above the floor, okay? And that would be greater than the distance above sea level, because we're above sea level now. So you have to specify what your reference position is. Now, I like to call it the zero reference position. And what I mean by that is the lowest level that object can go in the situation you found it. So if the lowest it can go in here is going to be the floor, that'll be my zero reference level. If it's going to be the tabletop, that would be my zero reference level. The podium, that would be whatever, okay? So you have to, or when you're talking about gravitational potential energy, it's the height above some reference level, okay? Now, if you choose the wrong level or your level changes, and you started off talking about the height above the podium, but then you move to there, if this was zero, that is now a negative potential energy, gravitational potential, because it's less than the potential energy here, okay? So you can have negative gravitational potential energy. If you choose your zero reference level right, then the minimum will be zero. But if you choose it and then the problem changes on you, you may wind up with a negative potential energy. And there's nothing wrong with it, okay? Absolutely nothing wrong with having a negative potential energy, okay? So, since that seems to be where we're starting here, let's give the formula for gravitational potential energy. Now, this book likes to just call this E sub P. I wish they said E sub GP for gravitational potential, because like we just said, there's bunches of different potential energies. Spring potential energy, which is also sometimes called the elastic potential energy, chemical potential energy, there's just lots of them. But when they say E sub P, they typically are meaning gravitational potential energy, okay? And that is mgh, okay? Now that looks a lot like a formula we've seen before, perhaps. Turn back a few pages here to 8.1. Now, We didn't actually express it this way, but we worked it this way. Whoops, wrong pen. There it is. Anyone remember what work was? That's capital W, work. What? Say that again. Okay, right. That's what work is when object first of all. Do you remember the formula for it? Force times displacement. And I think we used S for displacement. This book uses S, other books use D or other things like that, but S is fine. But what is the force when you've lifted something above a reference level? What force are you talking about? What force did I have to overcome to lift this book? This what? Okay, and what is the force due to gravity? What do we call that? I use it when I step on the scales. Say again? That's your force due to weight. So if this is your force due to weight, what's the formula for weight? Anyone remember that? Oh, please say yes. mg. Force due to weight is mg. mgs, if the displacement is vertical, then that's mgh. Hey, those are basically the same formulas, right? If the displacement is vertical, then mgs is the same as mgh, okay? So work would be increasing your potential energy if you're lifting something, decreasing if you're letting it fall. So there is your gravitational potential energy, very similar to your work formula with a stretch rate, okay? So E sub P is, they call potential energy, but in reality it's gravitational potential energy if you're using this formula. And the dead giveaway, now notice, mass is involved. The more mass the substance has, the more work I have to do, the greater potential energy it has. If I held this book above Rance's foot, or held this book above his foot, which you think he'd want me to draw? If I hold them the same height. This one, because this has less mass. So mass influences potential energy big time, but also, as we illustrated before, h, the height that I lifted, that influences gravitational potential energy. Now, how about that g? What's that? Anybody? It's the acceleration due to gravity. That's why gravitational potential energy basically has got to have the g in it somewhere, okay? And that has different values depending on whether you're in U.S. customary or SI units, okay? So the g here is a fixed number. That's not going to be a variable. Mass could vary between a light book and a heavier book. Height could vary on how high I lifted it, whatever, but g is either going to be 9.80 meters per second squared or 32.2 feet per second squared, okay? Those are the two possible values. Anytime you're on the surface of the Earth. Now, if you happen to be on the surface of the moon or somewhere else, send me a postcard, but no, most of the time we don't go there, okay? Most of the time we'll be on the surface of the Earth. Okay. There is a figure in your book, I wish they had on the PowerPoint, but they don't, is a crate that somehow you lifted off the floor into the air, probably with a forklift, however, they don't show, a height of h. Then you have done work on that, you've increased its potential energy, and it's calculated by multiplying its mass times acceleration due to gravity times the distance you lifted it, okay? If the floor is your zero reference level, which I think it would be, then the height over the floor would be it. So that leads us to example 1, top of page 215. Any questions so far? Well, yeah. Okay. A wrecking ball of mass 200 kilograms. So the mass of this wrecking ball is 200 kilograms. There's a bar over that second zero. What does that mean? That means that second zero is significant, meaning all three digits are significant. Three significant digits. It's poised 4.00 meters. That sounds like a height to me. 4.00 meters. Now that's taller than this room. That would be another meter, probably close to it, higher than the room. Okay, above a concrete platform whose top is 2 meters above the ground. So I'm going to see if I can draw this. Here's the ground. Here's the concrete platform. And this is difference here is 2 meters. And the wrecking ball is up here, another 4 meters above the top of the concrete platform. Now mine may not be the scale, okay? And by the way, I should put my significant, oh, yuck, I did it wrong. Okay. I hit the erase all, so here's, go back. I'll write the formula again, E sub P, which means gravitational potential energy, mgh, okay? Where G is either 9.80 meters per second squared or 32.2 feet per second squared. The others are variables, okay? And here we have the ground, the concrete platform, and this is 2 meters tall. And then we have the wrecking ball up here, 4 meters. I did it again. 4.00 meters above the concrete platform, and the concrete platform, get it right this time, is 2.00 meters. These are very precise platforms, okay? Meters above the ground. Yeah. Yeah. So the A part of the question here says, with respect to the platform, now I use abbreviation WRP, no, thought I did, WRT, I'm sorry, with respect to, okay, goodness, I can't even think tonight, with respect to the platform, okay, this is the platform. This is the floor, okay, or ground, they're calling it, the ground, okay. So with respect to the platform, okay, what is the potential energy of the ball? And what is the formula for potential energy? What's the symbol for it? E sub P, okay? And what's the formula for it? mgh. So relative, or with respect to the platform, what is the potential energy of that ball up here? And this ball is, oh, I had that. Mass of the ball is 200 kilograms. Okay. Now these zeros that follow a decimal, those are just about always significant, okay? So you don't have to put bars over those. So what's the potential energy relative to the platform? What's your mass? Not that hard. 200, the third digit is significant, kilograms. And what's your G? Which G do we use? You use 9.80 because you're dealing with meters and not feet, okay? So this will be 9.80 meters per second squared. And then what's your height above the platform? 4.00 meters. Okay? And what would this give you? That's 800 times 9.8. It's going to be something 7,000, really close to 8,000. Say again? 7,800 and what? 40? Okay. What unit? Don't just give me a number. Always have a unit with it. Say again? Joules. Very good. Kilogram meter squared per second squared, which is a joule. Same unit we use for work. Work is the energy is the ability to do work. Work is the use of energy. Same units. Okay? Is that last zero significant? Say again? No, we don't put a bar over that because we only have 3 digits coming in, only 3 digits coming out, so that 4th digit is not significant. We've got to have it there to make it 40, but it's not a significant digit. And they got 7,840 joules. Good for them. All right, the B part of the question then is with respect to the ground. What is the EP? Gravitational potential energy. Same formula, mgh. What differs here? So, yeah, the height is now 6. How far is it above the ground? 4 above the top of the platform. Platform is 2 meters above the ground. So you now have 200. I keep wanting to make that 400. Okay. I wanted a bigger wrecking ball. Okay. 200 kilograms, that 3rd digit being significant. And we still use the same G, 9.80 meters per second squared. And what's the height now? 6.00 meters. Someone punched in that on your calculator and see what you get. Be 1,200 times 9.8. It's going to be 11 something another. Pretty close to 1,200. 11,040. 040. 11,000 what? 750. Okay, let me correct to that. 750? 760. Okay, wait. Yeah, we'll get there. 760, what units? Joules. Okay, but what seems to be wrong with this picture? Too many significant digits. So how do we adjust that? You have 3, 3, and 3. So count up 3. 1, 2, 3. Look to the right. That's a 6. It's greater than 5. So therefore we round the 7 up and make it 11,800 joules. Okay? Now, if that's too big a number for you, and you want to use a smaller number but a bigger unit, what would that be? Anybody? What's the metric prefix? It stands for 1,000. Say again? What's 1,000 meters? Kilometer, kilometer, okay? So that'd be 11.8 kilojoules. This one up here you could have written as 7.84 kilojoules. You just move your decimal 3 places and put K instead of just the unit, kilojoules. Does that make sense? Now that's the one and only example they give you for gravitational potential energy. We will be coming upon this again in other problems, but they'll be compound problems, they're moving now to kinetic energy. All right, to go there, change the slide. Everybody got this? Okay. Kinetic energy now I like to call it KE. The book doesn't. The book likes to call it E sub K. All their energies always are E's, and then the subscript indicates which kind. E sub W is energy due to, force F sub W is due to weight, but E sub P is potential, which they mean gravitational potential energy. E sub K is kinetic energy, okay? Is due, always due to the mass, okay? If I were to throw a ping pong ball at you, you think you're going to need a glove to catch that? Probably can't even get it to you, okay? It wouldn't take much to stop that. But if I threw a bowling ball at you, I think I'd just get out of the way, okay? Because the mass is important. More mass, more kinetic energy, okay? So kinetic energy also depends on mass, but it also depends on velocity. And it's not just velocity, it's velocity squared. And I think I may have mentioned to you earlier, most of the time when your variable has an exponent of 2, you're going to have a coefficient of 1/2, or 2 in the denominator anyway. There's your formula for kinetic energy. 1/2 mv squared. Where E sub K is kinetic energy, m of course is mass, and now v is velocity. Okay. Now quite often we will use speed as if it's the same as velocity, and there's a reason for that. Just like work, energy is a scalar quantity. So we really don't need the vector characteristics of velocity, we just need the magnitude, or its speed. But the book calls it velocity, we'll keep calling it velocity. But actually speed works quite well too. Okay. Now, they're jumping into an applied problem here, and this is a pile driver, okay? Y'all know what I mean by a pile driver? Have you ever seen them when they're putting in the foundations of a building or a bridge or something like that? You'll probably hear them doing it. Yes, they're lifting some real big heavy weight up and letting it fall, free fall, onto the top of the piling, and that's driving it into the ground, okay? Now, before doing anything with kinetic energy, they're going to apply it to a pile driver, okay? The energy of the driver is the kinetic energy as it hits the top of the pile, okay? But the work done is then how far you move the pile, okay? So then the kinetic energy, the energy with which you deliver that, whatever the mass is of your pile driver, that's equal to the force times displacement of your pile, okay? And that's the formula they give at the top of page 216. I wish they had just dealt with some problems with kinetic energy alone, then gone to the issue of the pile driver. But they've done it, so we'll do it. Example 2 is a pile driver with a mass of 10,000 kilograms. So the mass of the pile driver is 10,000 kilograms. That's pretty heavy, okay, or pretty massive. The third zero is significant. They put a bar over that. It strikes a pile with a velocity of 10 meters. So the velocity of the pile driver is 10 meters per second. 10.0 meters per second. Okay? The A question here is, what is the kinetic energy of the driver as it strikes the POW? So what's the E sub K, that's what we're looking for here, of that as it hits the POW? What would that be? What's the formula? 1/2 mv squared. 1/2 is 1/2. It has no units. It has as many significant digits as you need. You could use 0.5. You could use 0.500000. Doesn't matter. 1/2 is exactly 0.5. Multiply that by the mass, which is 10,000 kilograms. And then multiply that by the velocity, which is 10.0 meters per second, but the velocity is squared. Okay? So if you carry this to its extreme, now what I'm going to do first is divide 2 into 10,000, and that gives me 5,000. And because that's a division, now the third digit is still significant. That middle 0 now is significant. Okay? But I've also got to, so this will be 5,000 kilograms times, and what is 10 squared? 100. Now that 0 is significant because you had 3 significant digits there. We have them here. And not only do you square the number, you square the units as well. Meter squared per second squared. Okay? And 5,000 times 100 would be 500,000, what units? Joules. Now I need to put a bar somewhere. Where do I put my bar? The which? Second 0. Absolutely. To give you 3 significant digits. Now if that's too big a number and you want to make a smaller number but a bigger unit, what would that be? 500 with a bar over it. What? Kilojoules. Perfect. Okay? All right. And they give them, but they do the first one in scientific notation, 5 times 10 to the 5th joules, or 500 kilojoules. Okay. So just to get you used to seeing scientific notation, if you're making this in scientific notation, you put 5.00, include all your significant digits there, times 10, and you're moving the decimal 1, 2, 3, 4, 5 places, 10 to the 5th joules. That's how you do scientific notation, if you ever need it or need to do it. Okay. So that's the A part. The B part says, if the POW driver is driven 20 centimeters into the ground, what force is applied to the POW by the driver as it strikes the POW? Whoa. Well, this time we're looking for force. What force? There's your question. We already know the the kinetic energy. That was 500,000 joules. So what we have now is 500,000, but I don't want to write joules. I want to write the fundamental units. And what are the fundamental units of joules? Kilogram meter squared per second squared. Kilogram meter squared per second squared. That's what a joule is equal to the force. That's what we're looking for. Now, is driving it 20 centimeters into the ground. So your displacement here is 20.0 centimeters. What's wrong with that picture? Yes, on the top we're dealing in meters, down here we're dealing in centimeters. So you got to convert one of these or the other to the other one, okay? Which you want to do. Any preference? So all your units are, the SI unit is meters. Let's get this 20 centimeters to meters. So we're going to need a conversion here. and that's a blank blank, and we're trying to get this to blank meters. Okay? Now, the first blank in that conversion factor is for numbers. Don't worry about that yet. Worry about the units. Always put the units in their place. Which unit goes on top of the line, which goes beneath the line? Which one? I can't hear well. You probably said it right. Which one? I can't hear. Say it loud. Centimeters where? On bottom. Okay, perfect. Centimeters on the bottom, that puts meters on the top. Now you worry with the units. How many meters are in a centimeter, or how many centimeters are in a meter? Anyone know? Okay, did I hear 100? Which one? Okay. Okay, think of what else starts with centi or cent. Can't dig one out. A penny is a centi dollar. How many pennies make up a dollar? 100. So it'll be 100 centimeters in 1 meter, right? So if you divide 20 by 100, you basically move the decimal 2 places to the left, and that gives you 0.200 meters. That's how far you displaced the POW. So that would be times 0.200 meters. Now we can divide by, if we're trying to get force, how much force did it strike it with, divide both sides by 0.0200. So I'm just going to do it here. 0.200 meters. Divide this by 0.200 meters. Now, the meters will cancel one of those meters out. That's why I want it in fundamental units, so you can see what's happening there. Okay, now you have to divide 500,000 by 0.2, basically. And you can either do it thinking your way through it, or you can do it on a calculator. I'm going to do it thinking. I'm going to put a 0.0 here, move this decimal 1 place here, move that 1 place there, so it's the same value. And then 2 will go into 50, 25, and then follow that by 1, 2, 3, 4, 5 zeros. So what would be the force? 2,500,000. What's the unit for force? Newton, okay? And a Newton is a kilogram meter per second squared. So that would be a Newton. Now, if that number is too big for you and you want to do a smaller unit, a smaller number but a bigger unit, what would that be? Oh, I also need a bar somewhere here. Not that I'm thirsty or anything, but okay. How many significant digits do we have? So where do I need to put my bar? Over that first 0. Perfect. Okay. Now, let's convert that to a smaller number but a bigger unit. What would that be? Anybody? Anyone know? 2.50, and you don't need a bar over that one because that's after a decimal. What did you say the unit was? Okay. My hearing's so bad I can't make out what you said. Oh, okay. You can do that. That's not to a bigger unit. That's just scientific notation, but that's fine. Times 10 to the 6th Newton. That's one way to express it. How would you do it with a that number, 2.50, but use a metric prefix rather than 10 to the 6th? Anyone know what that metric prefix is? Mega Newton. And anytime you get 10 to the 6th or higher, you capitalize the prefix. So that would be meganewton. Most of the time you don't see it written that way. So don't sweat it. Now, if you're talking about megahertz or megabytes or megajoules or something like that, yeah, maybe. Most of the time we don't use meganewtons. I don't know why, but they just don't. So that's probably why they left it as 2.50 times 10 to the 6 newtons. Okay. Any questions on that? You got to go? Okay. Well, I've got to find out what I did with them. There. No, that's not it. Here they are. All right. Again, anyone who has to leave early probably needs to pick up a test before you go. Okay. I think all these are generally in good shape. But listen to the YouTube video in case people bring up questions. Okay. So anyone else who has to leave early, good idea to pick up the test before you go. All right. Now, any questions on that? Okay. Let's go to example 3. All right, to erase. A 60.0 gram bullet. What in the world does that measure? 60.0 grams. What is that measuring? Say again? Mass. That's measuring mass. A 60.0 gram bullet is fired from a gun with 3,150 joules of kinetic energy. 3,150 joules. That is your E sub K. That's how they put it. I like KE better, but they like E sub K. Now, what seems to be a little wrong with this picture? Okay, what? Okay, and that's what the question is, find the velocity. So, yeah, you're reading ahead. Velocity. That's what we're looking for. Okay? But what seems to be an issue here? Second, your grams, because joules are kilogram meters squared per second squared, not grams. So what would be a good idea? To convert the grams to kilograms. In so doing, what do we do first? Do we try to guess on numbers? We put the units in their place. So what unit goes where? Grams on the bottom, kilograms on top. And now we ask ourselves, how many kilograms in a gram or how many grams in a kilogram? What is it? Say again? 1,000 kilograms is 1 gram? Oh, I hope so. Okay. 1,000 grams is 1 kilogram because kilo means 1,000. So kilograms mean 1,000 grams. Okay. On the street, a kilo, never mind. We won't go into that. Okay. Now, how do we do that division? We move the decimal place 3 places to the left. 1, 2, 3, because you have to move it for every decimal. So this would be 0.0600. You have to have those 3 digits after the 6, because those first 2 zeros are not significant. Only beginning with the 6, and you put 2 more. Okay, so are we ready to go then? What's the formula that relates kinetic energy, mass, and volume? Does anyone know? Okay, what is that? Kinetic energy. Kinetic energy is equal to 1/2 mv squared. Okay, we're looking for the v. So that means we want to solve for v, right? Now, what must we do to solve for v? First step? Yeah, in other words, multiply both sides by 2, right? That's how you clear out the 1/2, right? That goes away, and you got 2e sub k is equal to mv squared. Now what you do, you're still trying to solve for v. That's what you're looking for. Divide both sides by the mass. Okay? And that gives you v squared is equal to 2e sub k divided by m. But I'm not really interested in what v squared is. I want to know what v is. So what's the next thing we've got to do? Take a square root of both sides. So that will be this. Now, is it plus or minus square root? No, your speed is always positive. Okay, so don't mess with the minus sign. So that gets rid of that. So your v is equal to the square root of 2e sub k over m, which is the square root of 2 times, what was our e sub k? E sub k, 3,150. Now I don't want to use joules, I want to use my basic units. And what are they? Joules is a kilogram meter squared per second squared. Okay? And that's divided by your mass is 0.0600 kilograms. All right? Now, there goes the kilograms. They're out of there. And I'm going to multiply 2 times that, and that would be 6,300 meters squared per second squared divided by 0.0600. Okay? You lost a unit in the denominator. So I guess I would do the division first and then take the square root. So what do you get when you do your division there? Well, 6 will go into 6. Okay, here's what I'm going to do. I'll move my decimal 2 places that way and 2 places that way. Okay, so now it makes more sense. 6 will go into 6, 1, 0, 5, and then I still have 0, 0, 0. Is that what you got? Meter squared per second squared. Now I've got to take a square root. I can't do that one in my head. I think it's around 300 and some. Say again? 324? All right. So we're saying 324 what units? Okay, because when you take the square root of the number, you also take the square root of the units, which is meters per second. So 324 meters per second. How did the book do? Oh boy, they got it right too, didn't they? Good for them. Does that make sense? Okay? You know how to do it on your calculator. Take square roots. Good deal. Now, they talk about compressing or stretching a spring, which I told you that's a form of internal potential energy. It's also an energy of position because you're moving the position of the spring. Robert Hooke came up with the formula for that. By the way, he was I think a contemporary of Isaac Newton. I think maybe a little bit older than Newton, but they didn't get along too well. Newton did get along with many people very well. But anyway, I'm not sure about that. But anyway, there he is. He measured the relationship in connection with the invention of a spring balance for a clock. So Hooke's law is discussed in detail in section 12.2. I think we do chapter 12. Yes, we do. Okay, so we'll get to that in 12.2. Okay, so we've discussed 2 types of energy, kinetic and potential. And keep in mind, energy has many other forms. Chemical, which could be chemical potential energy. Atomic, which could be atomic potential energy. Electrical, which is just electrical energy. Or you could talk about electrical potential energy. We'll cover that in a later chapter. Sound, we'll talk about later chapter as well. Heat we probably won't talk about, but that's a form of energy as well. So the problem set for 8.3, I would do either 1 or 3 or both. Those answers are in the back. And then any of the odds 5 through 21. Those answers are in the back. So do as many as it takes for you to feel very confident that you know how to work these problems. Okay? Any questions? 8.3. Energy, yes.
So how did you get 324 from 105,000?
Okay. I listened to Madison. No, okay. How to do it? You get your calculator and you do 105,000 and then take a square root of that.
That's it?
Yeah, that's it.
And it just goes to meters per second?
Yeah, okay. And you take the square root of the units as well. They were meters squared per second squared. Take a square root of meters squared, you get meters. Square root of second squared, you get second. Meters per second. Okay, now I bet you that number had some decimals after it. But whatever the decimal was, you rounded to 3 significant digits. Okay, okay. Did that answer what you meant? Okay, good. Any other questions? Good questions, by the way. Okay. Now, 8.4 is talking about conservation of mechanical energy. Okay, do you need to get a test before you go? Okay. Now, we haven't finished doing all these in class, but hopefully we will finish before the end of the time. So listen to the YouTube video to get those that we haven't covered in class yet. All right. And if we don't get to the end, you'll still have time next week. All right. Any questions, other questions on this one? 8.3. Okay. I only had 3 examples. I had 21 exercises, so lots of possibilities there. So let me erase all this ink and talk about something they call mechanical energy. Okay? Kinetic and potential energies are related by the law of conservation of mechanical energy. I'm going to shorten mechanical energy to ME. I don't like writing it all out. Now, I wish they had really started this way. Energy is always conserved. Total energy is always conserved. That means whatever energy you start with, you're going to end with. Now, you can change forms, oh goodness, lots of different ways. But what it means to conserve energy is you can't get more energy out of a system than you put into a system. You just can't happen. Energy is conserved. Mass is conserved. You can't create mass, you can't destroy mass. Okay? Velocity is not conserved. You can change the velocity without, any problem. But you can't change energy. You can't change mass. Okay? Now, mechanical energy is often conserved. As long as you don't have anything that's, say, heating up the system, cooling off the system, anything. If all you have is changes of position and changes of speed, then mechanical energy is conserved. Potential energy is not conserved. Kinetic energy is generally not conserved. Only the sum of the two. So here's the law of conservation of mechanical energy. Here's what it is. The sum, what does that mean? You add them together. The sum of your kinetic energy, which this book calls E sub k, and potential energy, and what does this book call that? E sub p, in a system. So here we're not necessarily talking about individual objects, but it could be, but in a system is constant or conserved. It does not change if no resistive forces do work. And in the last chapter, what resistive force did we run into? Friction. As long as there's no or at least negligible friction, then law of conservation of mechanical energy holds. Frankly, you never get rid of friction, you minimize it. If you lubricate well, then you might get rid of most of your friction. If you're going at low enough speeds, air resistance, there's not much friction from air, okay? Higher speeds, though, you get lots of friction from air. So as long as you control your system, you might be able to use the conservation of mechanical energy. So here we're back at a pile driver, okay? Now I'm going to leave this screen. Can I leave it? Everybody got that? Okay. I'm going to discard this to go back to the PowerPoint. Oh, we finally hit a PowerPoint, okay? And here's what we got. A pile driver shows this energy conservation. When the driver is the highest position, sitting too long. Okay. When the crane has lifted this pile driver, remember that's a really massive thing, lifted it to the maximum position. Now it's inside a chute here that keeps it from wandering, but hopefully you've lubricated that chute so you don't have any frictional loss, okay? And you raised it up as high as you can. Right before you release it, what is the kinetic energy? You haven't released it yet. Is it in motion? No. No motion, no velocity. So your kinetic energy is zero. But you've got the maximum potential energy because you're not going to lift it any higher. So your maximum height here means you're at maximum potential energy. As soon as you release that thing, it's going to fall and hopefully not have any resistance, no friction. It's going to fall down here and strike the pile. Now, right as it strikes, now as it's fallen, it's losing its potential energy because the height is decreasing, but it's gaining kinetic energy because as it falls, it picks up speed, okay? Because if I were to lift, something I can lift without messing up too badly, okay? Lift this book, doesn't have much mass, but it has some. What's this velocity right here, right before I release? Zero. And when it falls, the maximum speed is going to be right before it hits. It was increasing speed all the way down, okay? Especially if I turned it on edge, because that one had some air resistance. But if I dropped it this way, it will go even faster. But all my papers are scattered, so I don't want to do that, okay? So we'll leave it like that. Or, do it with a pen, okay? The pen, that's position, no kinetic energy at all. It's not moving. Greatest potential energy. But when I release the pen, initially zero velocity, but as soon as I release, it picks up speed until it hits the ground and then probably broke my pen, okay? Okay, good. So, on its way down, it's converting potential energy into kinetic energy. And then, when it hits the pile, it takes that kinetic energy and does work on the pile and drives it down just a little bit, okay? So that's doing the work, just like our previous example was. Does that kind of make sense? Okay, so the second half of this picture shows right when it hits. Now, remember, the top of the pile was our zero reference level, so there the potential energy has gone to zero because you're at as far as you can. But now the kinetic energy is the maximum because that pile driver was the driver was picking up speed all the way down, so it was gaining kinetic energy all the way down till right when it hits. Then that impact, it drives the pile down, doing work on the pile. The same amount of kinetic energy it picked up, potential energy it lost, that's the work it's doing on the pile. Okay, that's at impact. Okay. Now, they show you, I wish this were on the same picture like it is in the book. The let me get my pen set up. The EP max at the top has to be the same as EK max at the bottom because mechanical energy is conserved. Mechanical energy is the sum of these two, zero kinetic, so it's all potential. It's also the sum of these two, zero potential, all kinetic, so those two have to be the same. So E sub P at the top has to equal E sub K at the bottom because mechanical energy is conserved as long as there are no friction losses. Okay? Now, what was the potential energy at the top? Remember the formula for potential energy? That was a long time ago, but remember what it was? mgh, where h was the height that it dropped. Okay? And what was the kinetic energy at the bottom? 1/2 mv squared. Okay. There's the formula that relates the two of those together. Okay? Now, guess what, folks? The mass doesn't matter. Well, it matters on how far you drive the pile, but there's mass on both sides of the equation. You could divide them out. Now, if you're interested in what is the velocity with which it hits, then we can do this. If we're wanting to solve for velocity, first multiply both sides by 2. So you get v squared is equal to 2gh. And now do what to get v? Take square root. V is equal to the square root of 2gh. Okay? The mass doesn't matter. Okay? It matters to how far you drive the pile, but it doesn't matter in our conservation of mechanical energy. And what is g, by the way? 9.80, what units? Meters per second squared. That's if you're in SI units, and if you're in the other set, US customary, that would be 32.2, what units? Feet per second squared. That does it for it. Okay? And the h is the height above the reference level, which usually is the top of the pile. All right. Does that make sense? Okay. I think I'll use this slide here to do example 1. A pile driver falls freely, meaning no friction, from a height of 3.50 meters above the pile. So that would be this h right here, 3.50 meters above the top of the pile. That's your h. What is the velocity as it hits the pile? So we're looking for v. Remember the formula we just derived? Or you can go back and drive it again if you want to. What was it? The square root of 2gh. Okay, you got h. What g do you use? 9.80 meters per second squared, because this was in meters. If that had been in feet, we'd use 32, okay? 0.2 times the height of 3.50 meters. And what does that give us? Now, you can do it all at once, or you can multiply those together. That's going to be about 7, almost 70, 66, 67, something like that, inside the radical. What you get when you multiply 2 times 9.8 times 3.5? Anybody? Say again? 68.6. Take the square root of that, and what do you get? And this will be meters squared per second squared, and this is about 4 something, did you say? No, I mean 8 point something. 8 point what? Wait just a second, I messed up my writing. Okay, 8 point what? 28? Okay, and what units? Meters per second, which is an excellent unit for velocity. So 8.28 meters per second. Perfect. Because you take the square root of the units as well. Square root of meter squared is meter. Square root of second squared is second. So you get meters per second. Does that make sense? All right. Now, another application or example or illustration of conservation of mechanical energy comes from something we call a pendulum. Okay? Now, there's a little something wrong with this picture, but we're going to use it anyway. Most of the time, a pendulum works when you have small angles. 65 degrees is a pretty big angle. So, but let's just pretend this will work for this angle as well. Now, what we have here is a pendulum, a mast at the end of a rod or a string or a cord or something like that that's been lifted. Okay? Now, when it's lifted like that and held in place, what's its velocity? Say again? What? 0, of course, because it's held in place. So its kinetic energy, because the velocity is 0, that's going to be 0 up there. The potential energy is going to be at its maximum. Now, what is going to be the value of that potential energy? Not in a number, but in a formula. What is the formula for potential energy? Anyone remember? Mass times acceleration due to gravity times height. Now, what's the height here? Is it height above the floor? Probably not. Now, I don't have a good way to do this, but I'm going to estimate this pendulum coming down here, and that rod appears to be maybe about that long, would you say? Did I overestimate or underestimate? Does that seem about right? Okay, let's just say that's our end of the pendulum there. Okay. There's the height. How far did it go from the maximum to as low as it could go on the problem? This is our 0 reference level. Okay? That's as low as it can go. Let that be our 0. So how far up did it go? That's your H. From that level. Not from the ground. Okay? That wouldn't make sense. It's not ever going to reach the ground. How high can it go? What's the lowest it will go in this problem? And that will be that. As long as your rod doesn't break. And let's hope it doesn't. So that's going to give you your H, and that's going to give your potential energy. Okay? Now, what happens as that pendulum, once you release it, what does it do? It falls, okay? You have nothing holding it up anymore, so it falls. As it's falling, what's happening to the kinetic energy? It's increasing because it's picking up speed. What's happening to the potential energy? It's decreasing because the height is decreasing. What will be the potential energy down here? 0, because now its height is at its lowest level. What would be its kinetic energy? Exactly what potential energy was. Because down here, potential energy goes to 0, kinetic energy goes to the same. doesn't matter, that near the same height. It's that amount right there. Because mechanical energy is conserved. The sum of the potential and kinetic has to be the same. Okay. Now, all this depends on a couple of things. Number one, this pivot up here, we hope is very well lubricated. So there's no friction loss there. There's always a little friction, but we're hoping it's not going to be much. Okay? The other thing is, we hope that pendulum, and okay, what does this remind you of? Where do you see a pendulum occasionally, maybe? A clock. A grandfather clock, a grandmother clock, something like that. That's a good example of a pendulum. Now, think of how some characteristics of that pendulum in there, okay? It's usually pretty big around like this, but how does it look this way? Really thin. Why? It's trying to reduce the air resistance. And also, it's usually in a glass box, isn't it? Because you don't want any airflow in there. There's going to be air in there, but you want that not to be moving. So you do everything you can to minimize the air resistance here, minimize the friction there, so this works. Conservation of mechanical energy. Okay. But this pendulum, now most grandfather clocks are not that big, they're like this, so you only pick it up a little angle, okay? Not 65 degrees, but that's okay. All right, now, when you release it here with no kinetic energy, no velocity, and release it and it starts falling, starts increasing its velocity till it gets here. Here the velocity is the maximum. Because your kinetic energy is the maximum. Potential energy is going to zero. However, because the velocity is the maximum, guess what happens when it gets here? It goes up this way because it has speed. It's not going to stop. There's nothing to stop it. So it's going to come up here. But as it comes up here, because it's on this rod, it's going to start doing what? Decreasing in speed, decreasing its kinetic energy, and increasing its height. So it's increasing its potential energy. How high does it get to over here? Exactly the same height it was there, as long as the mechanical energy is conserved. No friction loss there, no air resistance there. It's going to reach this height again. And then it'll stop. And then what will it do? Start falling again and doing the process over and over again. Mechanical energy, always the same. Potential energy, changing constantly. Kinetic energy, changing constantly. Mechanical energy, conserved. Always the same. Okay. Now, see if they have another picture here. Oh, here's one. How far has it fallen, apparently? About half the height. So guess what? It's lost half of its potential energy, therefore that went to kinetic energy. So now they're 50-50. Next one. It's reached as low as it can go, so its potential energy is 0. All the potential energy it had up at the top, now it's all kinetic energy at the bottom. Does it show it again? Oh, and it keeps on swinging. How high can it go? Only the height that it had to begin with. Now, how can this be changed a little bit? Let's go back to the beginning. What if you didn't release it, but you threw it? Now you're giving it some kinetic energy up there, because if you throw it, if you really push on it, you've given it kinetic energy to start with. Whatever is the initial speed that you threw it, that would be it. Then it could go higher over here, because it has more kinetic energy here. It will go up until it loses all that. Now, that's what they sometimes, I don't know. I'm not a roller coaster fan, okay? Are you? Yeah, okay. Do they give that a push, or does it start from scratch? ever ridden a roller coaster? Does it give it a push? Or does it just start rolling gradually? Huh? Okay, if they give it a push, that means you can go higher than you start here to get to the top of that loop-de-loop, okay? If you give it a big enough push. Okay, so that's not a perfect pendulum by any means, okay? But you can make it go higher if you give it an initial velocity. Okay. Now, all right. Oh, there's your roller coaster. Oh, you liked it, didn't you? Okay. Example 2, I really don't want to do completely. And I think you'll see why in a minute. Okay? Oh, wait, that's not what I want. I want to do that. No, I don't want that either. Okay. So let's go back to this one and go from current slide. Okay. Says drop a 5 kilograms, sorry, I misread that. Drop a 5 kilogram mass. I got to get my pen back. Okay. So your mass that you're dropping here is 5.000 kilograms. How many significant digits is that? 4. We haven't had many 4s, but we got one now. Drop a 5 kilogram mass from a hot air balloon 400 meters above the ground. So here's the ground down here. Here's the hot air balloon up here. You know, here's your balloon. Okay, and you're going to drop a 5 kilogram mass. So here's 5.000 kilogram mass. And this is, the height here is 400.0 meters above the ground. So your H is 400.0 meters. How many significant digits is that? 4, okay, above the ground. Find its kinetic energy. So we want to find KE. We want to find, wait, I'm sorry, I'm using my terminology. This book likes to use E sub K, sorry. So we're looking for E sub K, that's kinetic energy. It wants you to find potential energy, which is E sub P, gravitational potential energy, by the way, and the sum. And what's the sum of those called? Kinetic and potential? Mechanical. And I like to call that M, mechanical energy, E sub M. The book doesn't, but I'm going to call it that. Okay? And potential energy in 1 second intervals. Each second, okay, until it hits the ground. By the way, that's going to be 9.035 seconds. Now, you had no way of telling that. I was just looking at the answer here. Each second. So that means we've got to do 10, maybe 11 calculations for not just E sub K, we got to figure its velocity, right? We've got to figure its height, right? So we've got a lot of calculations to make, okay? So let's get started. The first column here is the time in seconds, okay? And we're going to start here at 0 seconds, 0.000 seconds. Then we're going to do it 1.00 second. Then we're going to do it at 2.000 seconds. 3, 4, 5, 6, 7, 8, 9, and we know it's going to stop about 9.035. They just told us that. Okay, that's first of the time. Now, here's a couple of things, okay? When you release it from here, the distance that it's fallen this way is S. The height is how far it is above the ground here. So this would be H, so many seconds later. So as S is increasing, H is decreasing. Does that make sense? Because sometime later it's going to be here, sometime later, well, it's going to be here, then it's going to be here, then it's going to be here. So at each second, it's going to have a different S and also a different H left to fall. Okay? So both of these are variables. So the first thing we got is your S here, how far it's fallen out of the balloon. So that's going to be in meters. And we'll also calculate its speed in meters per second. Okay? We'll also, from that, calculate the E sub K, that's the kinetic energy, because we know its mass already and we know its velocity then. Okay? Then the next thing we'll calculate is the height. That's the difference between S and the initial height, 400. So this will be also in meters. And then we'll do the E sub P because we'll know what we need there. And that will be, oh, and by the way, E sub K was in joules. And E sub P will be in joules. And then the total, which I'm calling E sub M, that will also be in joules. And you want to do this for 10 or 11 entries, right? Yeah, right. Okay. Let's just do a few. Okay. At the very top, and now notice here, it says drops, okay, a 5 kilogram mass. That doesn't mean throw it. You're not giving it initial velocity. You're dropping it, meaning its initial velocity is 0 because you're dropping it from rest. So at 0 seconds, it's still up there. So how far has it fallen? 0 meters, right? What's its velocity up there? When you drop it, 0.000 meters per second. What's the kinetic energy up there? 0.00 joules. How high is it above the ground? .0 meters. Okay, I'm not doing the units. What is this potential energy up there? Can we do that? What's the formula for potential energy? mgh, and that would be, what's the mass? 5.000 kilograms. What's G? 9.80 meters per second squared. And what's the height up there at the top? 400.0 meters. Okay, so that would be 2,000 times 9.8. That's going to be about 19,000 and some odd. What do you get? 19,600. What units? Joules. Okay. How many significant digits we have here? Nope. Look at there. You only have 3 for your G. Even though you had 4 for your M and 4 for your H, you only have 3 for the G, so it's just those 3, 196. Why they gave you 4, I don't know. You only have, and they put on here as if you did have an extra digit. I don't know why, okay? So they did, so I'll put it down to 19,600. They put a bar there. It's not legitimate. What was your mechanical energy? It's 19,600. And they put a bar over that too, and that would be in joules. Okay, 1 second later. How far did it fall? Ooh, how do we get that? Not in this chapter. Does anyone remember the formula for S? One half GT squared. Right? Remember that from before? If you look in your book, use 1/2 GT squared to find the distance the mass falls from the balloon. So that would be 0.5. I'm going to do it that way. I don't know. I'll use 1/2. It's easy too. One half, and what's G? 9.80 meters per second squared. And what's your T? 1 second. And 1 second squared would be 1.000 seconds squared. I went on and squared it. Is that okay? Okay. Well, half of 9.8 is 4.90. And that would be times that. So your height that it fell was, and see the second squared cancels out that second squared, and that leaves you 4.90. Now, do they put no? This is that drives me nuts about this problem. Okay? They then dropped it to there are 2 significant digits there. Why? I don't know. Okay? You obviously have 3. Okay? So it should be 4.90 meters. Okay? What is the velocity then? So here you have to use another formula. V is equal to GT. Acceleration due to gravity times your time. So that would be 9.80 meters per second squared times your time, which is 1.000 seconds. Okay? One of these seconds down here cancels out that second, and that gives you 9.80 meters per second. And in the book, they rounded it to 9.80. They got that one right finally. What's your kinetic energy now? What's the formula for it? 1/2 E sub K is 1/2 mg m what? V squared. Okay. Get carried away with my mg's. Okay. Okay, we got a velocity now. We got the mass, so it's 0.5 times 400 times 9.8. Someone punch that in for me. I don't want to have to think through it. Oops, I said it wrong. It's 5 kilograms, sorry. 1/2 of 5 times, or 0.5 times 5 times 9.8 squared. Give me an answer. Anybody? 0.5 times 5 times 9.8 squared. A little louder?
240.
Yeah, 240. That's it. 240 joules. Okay? What's the height? In other words, how high above the ground is it now? It fell 4.9 meters. It was at 400 meters. So what will it be now? 3. Second? Yes, subtract the 4.9 from your 400, 395.4 right? 395.1 meters. What's your potential energy now? There it was, mgh. The mass is still mass. That's 5 times 9.8 times the height now is 395.1. A little louder. I can't. 19,360. Is that what I heard? Okay. Now, add that to our EK, kinetic energy, 19,360 plus 240, and what do you get? 19,600. There it is. Your mechanical energy does not change. And you can do this for every second until it hits the ground. Sounds like a good homework exercise, doesn't it? The rest is left to the student. Don't you love it when the book says that? You know. But you see how it works. You have to use your formula for each one of those columns to get it. And notice the time is increasing pretty quickly. I mean, time is increasing 1 second at a time. Your distance is increasing pretty quickly. Your velocity is increasing steadily. Your kinetic energy is increasing quite big because your velocity is squared. The height is going down pretty quickly. Potential energy is going down pretty quickly, but total mechanical energy stays the same. Okay? Does that make sense? Y'all want to do another second worth? Please say no. Okay, good. All right. So, all right to leave this slide? Okay, we'll go back to the roller coaster if I can get it to come up. That's not what I wanted to do. This is what I wanted to do. Okay. All right, we'll go to this slide. All right, there's our roller coaster. Now, I'm guessing, and just merely guessing, that you get in the roller coaster here and then something pulls you up to the top. Okay? And there's your starting point. Okay? Now, right there at the top, I don't know if they give you a push or they let you start rolling. It looks like they just let you start rolling. And if they do, that's as high as you'll ever go. You can't possibly go any higher. Because once you start rolling, you're picking up speed, increasing speed, until you get maximum speed right down here, okay? And then you can get up this high because that's less height than you had there, but you'll still have some speed, so then you do twist around, you feel like you're going to be thrown out, and you come down here, and then you reach here. Now, if they don't put on the brakes, you keep on going till you go here again, then you go around and around and around. But you can't do that. Have you ever heard a roller coaster? If you heard it, it's got friction, because that's the only thing that makes a sound. So they got to stop you here, otherwise you would only get somewhere up to here, and then you roll down backwards. Okay. Now, if they gave you a push up here, maybe you could make it back to the top. But after a while, you can't go any further, so they're going to have to stop you down here at some point. There's your zero reference level. That's as low as you can go in this problem. Okay. Now, I'm not a roller coaster person, so I don't know how that usually goes. Does it usually break you to a stop, or does it come gradually to a stop? Okay. Yeah. What's that? They do have, and they do break you. If they started up here, if the house was up here to begin with, then they probably could give you a push. You could go through all this and may make your way back here and just gradually stop. I don't know how they do it. I don't think they elevate you up here to begin with. I think they start near the bottom. So they pull you up to the top and then let you run. But conservation of mechanical energy is at play here, as long as you don't have any friction, but you know you got friction. If it's going, as you're doing around, you know you're losing some energy due to friction. Okay. They probably don't sound that bad, but that's what it sounds like to me. Okay. Now, I guess what they wanted you to do here, and this is just generally, if this is the maximum, up here you have maximum potential energy and minimum kinetic energy. Down here, at your reference level, you have maximum kinetic energy and minimum potential energy. If this Q is halfway between these two, then you have about 50-50. Looks like to me it's further down here than it is there, so I would say it's probably a little more kinetic and a little less potential. Okay. But you have some of both there. They indicate it's halfway. No, they don't. They just say PQ. Okay. Now, there is something else that's mentioned here, and I don't think it's a huge deal. Oh, whoa. Where is that slide? Oh, that slide is later, much later. Okay, so let's go to, whoa, this one. Okay, from current slide. There is a situation that we call an elastic collision. Let me get my pen back. Okay. In an elastic collision, now what does the word elastic mean to you? Okay, everybody says, I used to think it too, that means it stretches, right? Not quite. What elastic means, it returns to its original position. That if you do stretch it, it goes back. Okay? Think of the spring in a ballpoint pen. Do you remember when you used to be able to take them apart and that spring in there? Did you ever take them apart and start playing with the spring? And if you ever stretched it a little too far, if it didn't go back, you passed the elastic limit. Elastic means it returns to its original shape. Not that it stretches, but that it returns to its original shape. That's what we mean by elastic. So in an elastic collision, and can anyone think of an elastic collision? Okay. One. Okay. What are some of your favorite sports? Just name a sport. Basketball, right? An elastic collision is when that ball hits the floor, and when it comes back, it's the same shape of ball, isn't it? Now, if you had a very rapid camera that took a picture of that ball when it hit the floor, what would you notice? It actually flattens. But then it rebounds and comes back to its original shape. That's an elastic collision. Almost. It makes a little bit of noise, so it loses a little bit. Except for the noise. Okay? And some people really dribble hard, and it comes back hard, right? If you just let it bounce, yeah. How you know it's not elastic? If you just drop it and let it bounce, it doesn't quite come back all the way, but it does come pretty close. Okay? Name another sport. Even some you might not consider sports.
Football.
Second?
Football.
Football. Okay? When that kicker kicks the football, if you took a picture of that right when his foot hits the ball, you'll see the ball deforms, but it comes back to its shape, and it takes off. That would be pretty close to an elastic collision. And you don't usually hear too much there, so that's really close. Name another sport. Tennis, okay? Have you ever seen a picture of the tennis racket hitting the ball? If you have, you'll notice tennis racket actually bulges back and the ball flattens out, especially when Serena Williams hits that thing, you know, boy, she can pound that thing, you know. But when that happens, they both deform, but then they both spring back. That's pretty close to an elastic collision, okay? Golf, okay? When you hit a golf ball, believe it or not, that hard little golf ball almost flattens against that club head, especially if you hit it with a driver really high speed. It almost flattens, but then it comes back off. That's an elastic collision, okay? All samples of elastic collision, they return to the original shape. It's not that they stretch, it's they return to the original shape. Okay, an elastic collision, okay, the total kinetic energy, I like to put KE, I'm going to put KE. They like E sub K, but I'm going to put KE, of the system before the collision equals the total kinetic energy of the system after collision. Okay. Now, what we're talking about there is the, I got some bugs over there. Okay. What it is, let's take the golf club. I'm not a golfer. But let's say you're swinging that club and its total kinetic energy right before the collision, all of the kinetic energy is in the club, right? None of it's in the ball, because the ball's at rest on the tee. I never hit it, but okay. And you do, then the total kinetic energy of the club is equal to the total kinetic energy of the ball after the club stops. Now you follow through on the swing and that kind of stuff, but at some point it stops. Now all the kinetic energy is in the ball, because everything returned to its original shape. That's what we mean by elastic collision. Okay. Ooh, it's getting close, isn't it? Now remember, pendulum and those kind of things, kinetic energy isn't conserved. But in an elastic collision, and we're talking about right before it. Now, after the ball takes up and goes into the air, no, kinetic energy is no longer conserved. It's just right before the collision, right after the collision, that's when the kinetic energy is conserved. Okay? They talk a little bit about it, but we're not going to do much more. Problem set 8.4, do any of the odd number exercises 1 through 13. Now, the rest of the thing, and we'll go over this just briefly next time, the rest of it, there are no new problems. No new problems at all. But we'll start with 8.5 next time. Just talk a little bit about that, and then we'll move on to the next chapter. So y'all do want your test, right? So you can get started on them. Okay, I like it. Eager class. Yes, yes, yes. All right. Sorry. Oh, okay. I see the swap. Okay. Keep on. Okay. Yes. Oh, okay. Sorry. I don't hear that. Okay. Good deal. And have a good weekend. Of course, working on physics will make it a good weekend, won't it? Yes. Okay. We'll see you next week. All right, good deal. Thank you. Are you sure you didn't want to work on some of the rest of them? Okay. totally confused here. Okay.
So it's due in 2 weeks?
What's that?
The test is due in 2 weeks?
Yeah.
Okay.
Always do at least 1 week. And
Okay.
if you need more time, you can